Why is it that once an object reaches the speed of light, time itself stops flowing? Even if you brought a spacecraft capable of infinite acceleration, you still cannot exceed light speed. What secret lies behind orders? Remember, the speed of light is the ultimate velocity at which any known object can travel. At roughly 3,000 kilometers per second, light can circle the Earth 7 times in just 1 second. While this is unimaginably fast to us, in the universe it's almost mundane. For example, light takes about 8 minutes and 20 seconds to travel from the Sun to Earth. That means if the Sun suddenly vanished, we wouldn't know for another 8 minutes and 20 seconds. Reaching Neptune, some 450 million kilometers away, takes over 4 hours, and escaping the solar system, a distance of about half a light year, would take up to a year. Once we step outside the solar system to a galactic perspective, we find that light from distant stars can take hundreds or even thousands of years to reach us. In other words, when we gaze at the star-filled sky, we're actually seeing those stars as they were in the past. Even at light speed, it would take tens of thousands of years to break free from the Milky Way, and reaching other galaxies remains utterly out of reach. According to relativity, no object with mass can exceed the speed of light. In that sense, light speed is like an invisible cosmic shackle, firmly binding us to Earth. Given how special the speed is, how did scientists uncover the secret of light speed? Let us return to the year 1676. After astronomer Euler Roemer first measured the speed of light, humanity realized that light does not arrive everywhere instantaneously. Instead, they found it had a fixed speed and began relentlessly probing its nature. The Newtonian mechanics' absolute space-time view insisted that light speed is determined relative to the reference frame. For example, if you jump upward with force inside a speeding train, though you'd see yourself land back where you started to someone on the platform, you'd be carried forward at the train's speed. Thus, for observers on Earth, the speed of light would vary with time and with different motions. But in 1887, the Michelson-Morley Experiment finally lifted the veil on this monster of light speed. Initially, Morley's purpose was merely to prove that a medium called the ether existed in the universe to carry light through space, and thought that if a beam of light propagated with the ether wind, then its speed should increase and conversely slow down. But the results shocked the physics community of the day. In other words, one set of light waves arrives at Earth directly, colliding head-on with its atmosphere at speeds, while another set follows more slowly, chasing the planet from behind. Both measured at about 3,000 kilometers per second, even though Earth moves around the Sun at about 30 kilometers per second. To explain why light's speed remains entirely unchanged, only 20th century physicist Lorentz proposed the length contraction hypothesis. He argued that a moving object's length contracts along its direction of motion, exactly offsetting the change in the light's path caused by Earth's motion through the ether. He then derived the Lorentz transformations mathematically, and later Einstein, based on these formings, formulated the principle of special relativity. Einstein held that all physical laws are equivalent in every inertial reference frame, thereby rejecting Newtonian mechanics' concept of an absolute frame. By solving Maxwell's equations, he derived the principle of light speed invariance, namely that no matter which inertial frame exerts light propagating vacuum, its speed remains a constant and does not vary with the relative motion between the light source and the observer's reference frame. So that to explain this phenomenon, suppose you emit a beam of light from a moving train. To someone on the train, the observed light speed should be the light speed minus the train's speed. To an observer on the platform, it would be the light speed less the train speed. But in reality, both measure the light speed as 300 kilometers per second. This explains why you can never reach light speed, even aboard an ever-accelerating station. You are merely chasing the beam of light ahead. Other observers on Earth see the spaceship nearing light speed. Relative to the light itself, you remain stationary while it recedes from you at its unchanging absolute speed. And according to relativity, 4-dimensional spacetime is made up of 3 dimensions of space and 1 of time. An object's speed in 4-dimensional spacetime equals its combined velocities in space and time. The faster it moves, the slower its time passes. If you remain motionless in space, time will continue to flow at its normal, unaltered rate. Whatever you do, the total speed through time and space remains the same in any circumstance. Either way, it's distributive differs. This strange time dilation effect is vividly illustrated in the theorem stated. Due to the extreme distortion of spacetime around a black hole, in the Drude rapid spray only an hour length us, while people on Earth might have already experienced decades. And this also implies that even if you believe you are at complete rest, every second you experience constant motion relative to other objects. Moves forward through the time dimension at near light speed, and phantoms do exactly the opposite. They devote all their speed to the spatial dimensions, traveling at 3,000 kilometers per second.